Hi everyone, welcome to the channel. In this video we're going to go into an in-depth analysis about Euclid's fifth requirement. So let's jump in. So we left off on requirement 4, and before we get into 5 we need some preliminary definitions. So first we need to define a parallel line, and to be able to define a parallel line, first we need to define a secant line or chord. So a chord is any straight line that has endpoints, locations which are part of the circle's circumference. Definition of parallel line: if the arcs, these red arcs here in the diagram, formed by an orange chord on both sides of a perpendicular between the chord and the diameter are equal, symmetrical, then the chord is parallel to the diameter. Thus, to establish in a rudimentary fashion if different straight lines are parallel, either straight line must coincide or overlap at least partly over the diameter and the other over a circle chord or orange secant. So this is the diagram here. We have this diameter, this is the circle, and through the center this blue line is the perpendicular. So if we run a chord, and we define what a chord or secant is, up and down this blue line, which is perpendicular to the green line, which is the diameter, when these red arcs here are symmetrical or equal, then we can say that this orange line is parallel to the green line. So now we need to define a transversal. So now we need some more definitions and a theorem before we can derive the fifth and final requirement. We defined a transversal as a straight line which meets any secant line and a diameter in different points. So we defined the secant and the chord, and now we have yet another line that meets the chord and the diameter. So we're adding steps, we're adding complexity. So red lines are transversal lines, blue lines are chords or secant lines, and the green lines are diameters. We can call the point where different lines of an angle meet a vertex, since we also want to talk about angles, not at circle centers. So in this case we have the circle, the green diameter, a random blue secant, and a red line which we call a transversal, which meets these two lines. Another case is where this blue secant is parallel to the green diameter, and then a third random case. So once we've defined these lines, now we want to know what happens. We've defined a vertex, these points where all these lines meet, and we want to name these angles, the various angles that arise, and to see what the relationships of these angles are. So naming the angles. Given any two parallel lines and a transversal crossing them, we need to give names to the angles formed. We call the red and purple angles co-interior. So red and purple are co-interior. The dark blue and green angles are also co-interior, here and here. The black and green angles are called vertically opposite, so black and green. Finally, the black and purple angles are called corresponding, so black, and purple. Next we have to prove that the given pairs of angles are equal. So, proof 1. To prove that the black and green angles are equal is easy because a circle with center at the light blue point on the dark blue parallel line has the same radii, and by symmetry the arcs on which the black and green angles are subtended are equal. So black and green are equal because of symmetry of the arcs given this circle. So we can show similarly that the black and purple angles are equal because of equal circles with centers at the light blue points. See diagram. So black and purple, the black and purple angles are the same, because if we define a circle around here and a circle around here, these are exactly the same shapes. So unfortunately Euclid did not use the circle to prove these facts, but resorted in long convoluted arguments such as one finds in the propositions of Book 1. So second proof. The alternate green and purple angles are equal because they're both equal to the black angle. So the green and purple are equal because in turn they're both equal to the black angle. We know that the sum of supplementary angles are the same as that of a straight line, two right angles, by definition. If the light blue points are centers, the result is immediately evident. Angles with the same vertex that lie on a straight line are the definition of supplementary angles. Right. Moreover, we can prove that the sum of the co-interior angles, say red and purple, are equal to a straight line angle, which is two right angles, because the purple angle is equal to the green angle, because they're alternate, and the green and red angles are supplementary angles. So we're done. So now we need to define a triangle. So we're not ready to derive the fifth and last requirement. So a triangle is defined as that path which is formed by joining the endpoints of a secant line that is parallel to a diameter to another point on the circle's circumference such that the joint paths are straight lines. It's easy to show that for any given secant line there is a diameter line that is parallel. So again, note that I said nothing about number of points or vertices because I've not yet derived number. Also, there's no angle measure without the circle. Trigonometry is a specialized circular geometry. So in this diagram, the triangle path consists of blue, red and pink lines. So blue, red and pink lines. So this dynamic applet shows all these possible triangles. So now we need a theorem. So we know that a parallel blue secant line exists that is parallel to the diameter at the point where the pink and blue lines meet below the diameter. So the green line is the diameter, and there is a parallel blue secant line where these two lines meet, parallel to this secant line here. So since the black, red and blue angles have a sum that is a straight line angle, two right angles, so black, red and blue, black, red and blue have the sum of two right angles, it follows that the sum of the red, green and black angles must also be a straight line angle, because the green angle is equal to the blue angle. Alternate angles on parallel lines are equal, as we know. So yeah, this blue angle here is equal to the green angle. So the theorem just proved states that the sum of any triangle is equal to a straight line angle, which is two right angles. So now we're ready to derive the fifth requirement. So, fifth requirement. I won't read the ancient Greek for you. I'll just go to the English definition. Yet again, I'll state it, which is the fifth requirement states that the sum of co-interior angles on either side of a transversal crossing any two lines is constant, regardless of how the transversal crosses the same. So, as we've said before, since the time of Sir Thomas Heath, this is very poorly understood, if at all, by the mainstream, and the whole mathematics as a whole has gone down the drain because of the misunderstanding of this fifth requirement from Euclid. So, there's no definition about parallelism in this statement. In fact, the fifth requirement of the original Greek is stated without using the word parallel at all. So, how do we derive the fifth requirement from the previous four? Before I continue, the sum of angles does not require any arithmetic, only the joining of arcs on a circle circumference. So, the fifth requirement states that as long as the red line, this transversal, crosses both the blue and green lines, the sum of orange and red angles remains constant. As you can see here. Also, the sum of the blue and green angles remains constant. So to prove the fifth requirement is true is fairly straightforward. Since the green, blue and black angles are part of a triangle, their sum is a straight line angle, as we showed with the triangle before with our proof. Therefore, blue and green angles will always be supplementary to the black angle, and hence their sum cannot change. But the orange and red angles are supplementary to the blue and green angles respectively. Therefore, their sum also cannot change. And that's it. So, as you can see, we needed many slides to demonstrate the systematic derivation of the 5 requirements of Euclid. Using only straight lines, shortest distance, we can now complete the systematic derivation of the number concept, using the elements in these five requirements, incorrectly called axioms by Thomas Heath and those others in the mainstream. So for far too long, the false belief that axioms are necessary for mathematics prevailed. So we don't need axioms, we don't need the Zermelo-Fraenkel axioms to build mathematics. In this whole series, we've systematically, from nothing, built the 5 requirements of Euclid, and this is all that's needed to do all of mathematics in a complete and thorough and perfect way. So that's it. I'll create another playlist that follows this one and has to do with the derivation of number. So I hope you enjoyed this series, and I'll see you in the next one. Thanks, bye.